Can you see the screen?
Yes, ma'am.
Okay. So I was doing group action. So I have defined what is a group action as an application. We have done like every group of order p square will be abelian and those kind of things we have already seen. Today we will see some more applications of group action, and then we will start with Sylow's theorem. Okay, so application of group action. So just one query that is there any doubt on the portions that I have already covered? Anything that is not clear, you want me to go through once again? Is there any topics or something in the group action portion?
Ma'am, how to visualize the equivalence class? Say you give some examples like Mobius strip or this portion. More examples would be better.
Okay, so that examples I like to give an essence of how this equivalence class plays an important role in other areas, not only in modern algebra but also in topology and all those things. Just in order to connect these things I have given, like that is not the part of what I am teaching. Okay, so maybe those kinds of things you will learn when you will learn in your topology class, the quotient topology and all. In there, that things will be much more clear to you.
Ma'am, is there any relation with this quotient group? Because they are.
No, the thing is that in the quotient group, the object that I have considered there, like this Mobius strip is coming as the equivalence class and all those things, those are not having any group structure. Those are topological spaces. And in that topological spaces, we have defined some equivalence relation and identified the points which are on the corner in the opposite direction. And we constructed the quotient space to be that space. So that you will learn in that space you have a topological structure, not group structure. Okay. But in this course we are basically studying the group structure. So that's why I don't want to go much into that direction. Maybe in your topology course you will get to learn all these things. There you will study the topological structure of the space, and then the equivalent thing of the quotient group will be the quotient topology. Okay. Okay.
Thank you.
So yeah. So let's start with some. Yeah. Sorry.
Can you give example based on Kelly's theorem?
Yeah, we will see. Okay, we will see. Okay, so let's start with application of group action first. So couple of applications. The first thing is which is known as fixed point congruence. So this is one theorem. Fixed point congruence. So this group action is one thing that if you apply it in a proper way, then you can actually give alternate proof of many of the theorems. Okay, so what is this fixed point congruence theorem says? So it says that let G be a group, let G be a finite P group. Do you remember the definition of a P group? So a P group, just recalling, a P group is nothing but whose order is P to the power n for some n. Okay. So I'm starting with a P group acting on a finite set X, acting on a finite set X then it says that the cardinality of the set X is congruence to number of fixed points in the set, and this is congruence mod P. So what is a fixed point? So we say that X belongs to X is said to be a fixed point if X remains fixed under the group action G. That means G of X will be equal to X for all G belongs to G. Okay. So I have a group action from G cross X to X. Okay. So and a point of this set X is said to be a fixed point if Gx, that means I'm acting this group G on this set X, if Gx is giving me X for all G. Okay, not only just a single G, if all the group elements fixes this element X, then we call X to be a fixed point. And what does this theorem says? This theorem says that if your group is a finite P group which is acting on a set X, it doesn't matter what kind of set is this, what kind of group action is this. It says that the cardinality of the set will be congruence to equal to the number of fixed point. That means how many elements of this set are remains fixed. It is saying that it is equal to the cardinality of the set X if I go mod P. Okay. So this is the fixed point theorem. So we will prove this theorem using group action. Is the statement clear to everybody?
Ma'am, fixed point is something like kernel.
Fixed point is
Kernel for group action.
kernel of a group action. How we have defined the kernel of a group action? We have defined it to be nothing but the set of all elements that was for all S. Means GS is equal to S for all S, but here I am fixing a point S. Okay.
Kernel are element of G, man. Kernel.
Kernels are element of
G.
yes, kernel are element of G, and whereas this is an element of the so what let me recall the definition that it then it will create eliminate the confusion. So kernel of a group action was nothing but the set of all the elements of the group G such that GS is equal to S for all S in the set A. So you can see now the difference. It is a subset of the group G. It is the collection of all the elements of the group which fixes all the elements of the set, whereas this fixed point are elements of the set which remain fixed by all the elements of the group. Is this clear now, the difference between the kernel and the fixed point? The
Yes.
fixed point are elements of the set, whereas kernel is nothing but the elements of the group. So these two are completely different. They are not at all same. Okay.
Yes.
Yeah. So you have to be very careful. Each time you should recall the definition and understand them clearly. Okay. So now let us see a proof of this fixed point theorem. So what do we know? So we have a group action, and this is something related with the cardinality of the set. And if you have a group action, then how can you see this set? You know that this set is nothing but the disjoint union of the orbits of the group action, right? Correct? So let the different orbits of X are represented by x1, xt. Then what do I know? That this x can be written as, okay, let me just, then this x can be written as disjoint union of the orbits. This is true, right? For any group action, the set can be written as disjoint union of its orbits. Correct? Now, what are the cardinality of the orbits? Then we can see that the cardinality of the set is nothing but the cardinality of the sum of the orbits. Correct? Now, what is the cardinality of the orbit?
Index of stabilizer.
Index of the stabilizer. So G colon stabilizer of xi. Okay. Now, this is nothing but order of G divided by order of the stabilizer. We already seen the stabilizer is a subgroup. So now our G is a P group. That means what? That order of G is P to the power some integer. So then what are the choices for this order of the orbit? This will be either
1 or p to the
power of P, or it has to be 1. Okay, because it should be the divisor of order of G, and divisors of order of G is nothing but P to the power something. This is because G is a P group. Okay, fine. Now, if the cardinality of the orbit is equal to 1, what does that mean?
X1 is a fixed point.
Yes. If the cardinality of the orbit is 1, that means what? This means that this means G is nothing but the stabilizer of xi, right? That means all the elements of the group are fixing xi. That means xi is a fixed point. This implies that xi is a fixed point. Okay. So now this equation, let it denote by star. Okay. So if I go mod this equation star, then what do I get? So going mod P, the equation star, we get, what do we get? All of the cardinality of these orbits are either 1 or it is P to the power something. Okay. Now if I am going mod P, then what will happen? That those orbits which are having cardinality P to the power I, those will vanish, right? Only the orbits which are having cardinality 1 will survive, but cardinality 1 means nothing but the fixed points. So this will give you nothing but number of fixed points. Is this clear to everybody?
Hello, ma'am.
Yes.
Ma'am, please the last line.
Yeah. So what I'm saying, so this much is okay up to this statement. That if the cardinality of the orbit is 1, then xi is a fixed point.
Yes, ma'am.
Okay. So now go back to this equation. Okay. So what is the cardinality of the orbits? Either 1 or P to the power some integer. So now if I go mod P, this equation, what I will get? Those orbits which are cardinality is P to the power something, if I go mod, those will vanish, right? Those will not contribute
Hmm.
anything. So only those will survive whose cardinality will be 1 in this equation. Right?
Yes, ma'am.
And the cardinality 1 elements are nothing but the fixed points. So how many elements will survive here? As many as fixed points are there. Therefore, this I am getting this. Is this clear now?
Okay, ma'am. Yes, ma'am.
Okay. So this is the fixed point congruence theorem. This is one of the application of group action. Okay. Now let's see some other types of application. So should I go to the next page?
Yes, ma'am.
So the next theorem is says that any non-abelian group of order 6 is isomorphic to S3. Okay, so let us see a proof of this one. Any non-abelian group of order 6 is isomorphic to S3. Okay, that is what we would like to prove here. Okay, so let G be a non-abelian group of order 6. Okay. Now, what can you say about the subgroups of a group of order 6? What will be the cardinalities of its subgroups? What are the possible cardinalities?
2, 3, 6.
2 and 3. And by Cauchy's theorem, what do we know? For every prime divisor, there exists a subgroup of that order, right? So 2 and 3 both are prime divisors of 6. So that means there exists a subgroup of order 2 and a subgroup of order 3 in G, right? So by Cauchy's theorem, G has subgroups of order 2 and order 3. Say H and K respectively. That means H is an order 2 subgroup and K is a order 3 subgroup. Okay. Okay. So now this H is a order 2 subgroup. So I can write down H as, so H will be what kind of group? It has to be a cyclic group because a group of prime order is a cyclic group. So this H will be a cyclic group. So let H is generated by A, okay, and K will also be a cyclic group. Say it is generated by B because it is of order 3, such that order of A is equal to 2 and order of B is equal to 3. Okay. So now this H, can it be a normal subgroup? Can H be a normal subgroup of G? This is the question. G is a non-abelian group that I have started with. Now I am asking whether H is a normal subgroup of G or not. Can somebody tell me?
Yes, ma'am.
G will be a normal subgroup?
H will
H will be a normal subgroup.
yes,
Yes,
ma'am.
ma'am. H will be normal, but G. K. No, ma'am. No. H will be not.
Just hold on a second. Huh? Yeah. Okay, so what I was asking, so can H be a normal subgroup of G?
Yes, ma'am. It can be a normal subgroup.
No,
It
ma'am.
can be. No, ma'am. Okay. So why it is no?
Ma'am, if H be a normal subgroup and K must be normal subgroup
Yes.
and H intersection K equal to identity
Yes.
and HK all elements are commute each other
Yes. Then it will
and
become
it
abelian
will
group,
become
right?
cyclic or abelian and cyclic.
It will become abelian group in that
Yes,
case,
yes,
right?
ma'am.
But I have started with G to be a non-abelian group,
Non-abelian
right?
group. Yes, ma'am.
So H cannot be a normal subgroup.
Yes,
Okay.
ma'am.
So if H is a normal subgroup, then this BAB inverse, so maybe note that H cannot be a normal subgroup of G as G is not abelian, because if H is normal subgroup of G, in that case G becomes abelian. Okay, so why it is so? That follows from the fact that H and K both are normal and H intersection K is identity. So G will be isomorphic with H cross K, and these two are abelian. So G will also be abelian. Okay, fine. So that means H cannot be a normal subgroup here. Okay, because I have started my group to be a non-abelian group. Therefore, H is not a normal subgroup. Okay, but what will be the index of?
Ma'am, please show previous slide once again.
Yeah. What will be the index of H in G?
3.
3.
3.
That means there will be 3 left cosets of H, right? So now what I will do now, I will apply one group action on this set of left cosets. Okay. Should I go to the next slide now?
Yes, ma'am.
Okay. Now that is there are 3 left cosets of H in G. Now I consider the group action from G cross. This denotes the set of left cosets. H is not a normal subgroup. So this notation I'm saying the set of all left cosets of H. I'm not considering the group structure here. I'm just considering it to be the set of all left cosets to G quotient H. Okay. So how I'm defining this group action? Consider any element from the group and say H is an element of the set of left coset. So this is a left coset. Where I will send it to GH, which is again a left coset of H. Okay. So this is the group action. Is this group action clear to you? Is this group action clear?
Yes, ma'am.
Yes, ma'am.
Okay. So I take one left coset from the set of all left coset and just apply this element from the group G on this left coset and sending it to the corresponding left coset GH. Okay. And now I know the permutation representation of this group action. So the permutation representation of this group action will be what? The permutation representation of this group action is a map phi from the group to where it will be?
S3.
S3, because there are 3 elements in the set of left cosets, right? So I will be having the map from G to S3, the symmetric group with 3 elements. Okay. So now we know that this is a group homomorphism. What I want to show that G is isomorphic with S3, right? So I have already defined a group homomorphism. And what else I know? I already know the cardinality of G is same as the cardinality of S3. S3 has 6 elements, G also has 6 elements. So now if I am able to show that this map is 1, 1, then it will be a bijection, right? So what is the kernel of this map? What is the kernel of this group homomorphism? It is the collection of all the elements of the group G such that it fixes the left cosets, right? So in other words, this sigma G should be identity. If you remember this map. So G goes to sigma G, where sigma G is a permutations from S3 to S3. How this sigma G was defined? So this is using the group action. So it would be nothing but G left coset should go to the same left coset, right? The collection of all G such that GH should be equal to HG, right? Okay. So this is the kernel. Yes.
I mean, the proof of the Cayley theorem, we defined the function psi from G to S cardinality of G.
G to?
G to S n, where n is the cardinality of G.
Yes.
And here the cardinality of G is 6.
No. So what so in the Cayley theorem, see, the Cayley's theorem, I have considered a particular group action, isn't it? Where the set was itself the group.
Yes, ma'am.
There was no difference between the set and the group.
Yes, ma'am. It was left multiplication.
Yeah. But in general, if you see the permutation representation, then what was the, where I have, if you recall the permutation representation of a group action, then where I have sent it?
To sigma G.
I have defined this. Yeah, I have defined this map phi from G to SA, where A was the set.
Okay, ma'am.
Okay.
Okay, yes, ma'am. Got it.
Okay. Yeah. So for Cali's theorem, the set was itself group. So it was, you were saying that it was the cardinality of the group, but it was in fact the cardinality of the set, not the cardinality of the group. Okay.
Yes, ma'am.
Fine.
Yes, ma'am.
Okay. So now this is the kernel of phi. So now let us see the kernel of phi is what can be this kernel. I need to show that this kernel should be identity. Okay. So let's see that if some element is in the kernel, then what happens. So if G is in the kernel of phi, then it fixes the left cosets. So it fixes H as well. That means GH should be equal to H, which implies that G belongs to H. Okay. So that means kernel of phi, which is a subgroup of G, of course. Okay. So that means this kernel of phi is either 1 or H. But kernel of phi cannot be equal to H as H is not a normal subgroup. As H is not a normal subgroup. Therefore, what is the choice for kernel? It is nothing but the identity element. Okay. Therefore, I should have that G is isomorphic with S3. Is this clear?
Ma'am, could you repeat once in brief way?
Okay. So what I told that I would like to prove that any non-abelian group is isomorphic to S3. Okay. So for that reason, I need to define a group homomorphism from G to S3, and I tried to show that this group homomorphism is in fact an isomorphism. So in order to define a group homomorphism from G to S3, what I have used a group action, because I don't know what is the structure of G. Only information I am having is that G is non-abelian. Okay. So for that, I have considered this group action. How I have considered? So group is G and set is the set of all left cosets. So I am defining this group action where G is acting on the set of all left cosets, sending a left coset to the corresponding left coset GHH. And now using this group action, I have got this map, which is a group homomorphism, which I am getting by the permutation representation of the group action from G to S3. Okay. So now I have a group homomorphism from G to S3. Okay, and cardinality of G is same as cardinality of S3. Now, if I'm able to show that this map is injective, then I will get the isomorphism. In order to show that injectivity, I consider the kernel of this group homomorphism. So kernel is all the elements of the group such that sigma G gives you the identity permutation. Okay, that means sigma G of a left coset HH should go to HH. Okay, so this is the kernel. Okay, now if some element is in the kernel, then it should fix the left coset H itself, right? So in that case, GHH should be equal to H. So that gives me that G should be in H. So by keeping this that GH is equal to H, this gives me that this, if some element is in the kernel, then that element should also be in H. That means this kernel is a subset of this, or this kernel of phi is a subgroup of H. Okay. But now what do you know? H is a order 2 subgroup. No? Because H was generated by an order 2 element. So I have started with H to be a order 2 subgroup. So that means what are the choices for kernel of phi? Either it will be equal to 1 or it will be equal to H. But kernel of phi can it be equal to H? If kernel of phi equal to H, but kernel is always a normal subgroup, we know. But H is not a normal subgroup. That means kernel cannot be equal to H. So if kernel is not equal to H, then kernel has to be equal to identity. Therefore, we get this isomorphism. Now is this clear?
Yes, ma'am. Thank you, ma'am.
Okay, so now we will be using this group action from the set of all left cosets in the next 2 applications. We will see that this group action plays an important role if you would like to prove some theorems in group theory. Okay, so is this proof clear to everybody?
Ma'am,
Yes.
in the previous page, last step, we have written that GHH is equal to HH. From there, can you explain how you got the next line?
So this is the description of the kernel. Kernel is all elements which fixes all the left cosets.
Okay, ma'am.
HH is one particular left coset. You can choose this small h to be identity. That will give you the left coset corresponding to H, right?
Okay, ma'am. Understood. Thank you, ma'am.
Okay, fine. So now should I go to the next application? So the next application, we will be using the same group action. So let G be, maybe I should not write it as a corollary because it doesn't directly follow from there. I should put it as a proposition. So let G be a finite P group. Okay. Then what it says that any subgroup of G with index P is a normal subgroup. Okay. In general, it is not true because we have already seen that if, for example, in the previous case, we have this, we have H to be an index 3 subgroup, okay, where 3 is a prime number and 3 divides the order of the group, but still this H was not a normal subgroup. But if your group is a finite P group, in that case, if you consider a subgroup with index P, then it will be a normal subgroup. Okay, so it gives you the criteria when in a P group you can have, how you can have normal subgroups. Okay, so we will prove this using the same group action. So I will consider the group action from the group G to, so here let H be a subgroup of index P. Okay, so I'm starting with H to be a subgroup of index P, and then I'm considering the set of all left cosets. of H in G, and I am defining the group action as I have defined earlier. Any doubt? So here the set is nothing but the set of all left cosets. Here again this denote the set of all left cosets because I don't know whether H is a normal subgroup or not. That's what I want to prove, that H is a normal subgroup. So by this notation I am denoting the set of all left cosets of H. So what will be the cardinality of this set? The set of all left cosets of H. Your voice is breaking. What is H? H is a subgroup of index P. What does that mean?
That the orbital contain P.
Cardinality.
That means there are P left cosets of H, no? That
Yes,
means
ma'am.
this cardinality of this set will be equal to P, right? Is this fine?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. So now again, like the previous way, I have considered this set with cardinality P, okay, which is nothing but the set of all left cosets, and then I am applying this group action. So now what is the permutation representation of this group action will be? The permutation representation of the group action is phi is a map from G to S. Where should I send it to? Where it will be? What will is which symmetric group?
SP.
SP, right? Because the cardinality of that set was P. So this permutation representation will be a map from G to the symmetric group SP, right? So I have now defined a group homomorphism from G to SP. But you can see here that the cardinality of SP is P factorial, which is some number different from G. So how do I prove now? I would like to prove that H is a normal subgroup of G. So now what should I use in order to prove?
Try to show kernel phi is equal to H.
Yes, then it will become a normal subgroup because I already know that kernel of a group homomorphism is a normal subgroup. So if I am able to show that kernel of this group homomorphism is H, then I am done. Right? Okay. Now let's try to show that kernel of this is H. So let the kernel of phi denoted by K is a subgroup I already know. Okay. Now what do you know? So by first isomorphism theorem, I can say that G quotient K, the kernel, will be isomorphic with a subgroup of SP. Correct? Fine. This will be the isomorphic with SP. What does that mean? That G colon K will divide P factorial. Isn't it? G colon K is nothing but the cardinality of this quotient group G quotient K. The cardinality of this quotient group is same as the cardinality of the subgroup of SP. Now order of the subgroup divides the order of the group. Therefore, G colon K divides P factorial. Is this clear?
Yes, ma'am.
Yes, ma'am. Okay. Now, what do you know about G colon K? What are the possibilities for G colon K, given that G is a P group?
Then greater than equals to P.
It can be identity also.
Yes, ma'am.
Okay. So it is equal to 1 or a power of P. Correct. Isn't it? Okay. But now we have already seen that it also divides P factorial. So from here, what can I say? Can it be any power of P?
Only one power maybe.
Yeah. So G colon K will be either 1 or it has to be equal to P. Because of this fact, isn't it? Because it should divide P factorial, right? So either it has to be equal to 1 or it has to be equal to P, G colon K. Okay. Now, as previously we have seen that if I start with any element in the kernel, then that element fixes the left coset H itself. Therefore, G is in H. That says that K is a contained in H, isn't it? So if G is contained in H, then what can you say about G colon K? Can it be equal to 1? G is sitting inside H. H is a subgroup with index P. If G colon K is equal to 1, what does that mean? That means that G is equal to K. But K is sitting inside H. That means G cannot be equal to K, right? That means this index has to be strictly greater than 1. Is it clear?
Yes, ma'am.
If you are not able to follow, then please let me know. But don't remain silent.
How does that GH equals to H or K, G belongs to K?
Okay. So what was the kernel? Kernel was all the elements which fixes this left cosets. No? How was this group action? This group homomorphism, how it is defined? So here you consider G and send it to sigma G. How is this sigma G defined? Sigma G of HH is equal to GHH. Okay, for all the left cosets. That means sigma G of H should be also equal to H. Right?
Yes, ma'am.
What will, if some element is in the kernel, that means what? That means it will fix all the left cosets, right? So it will fix the left coset H itself. Then maybe sigma G of H should be equal to H. If I take any element in the kernel, then sigma G of H should be equal to H. Is this statement clear?
Yes, ma'am.
What is sigma GH? It is nothing but Hg, right? Is it
Yes, ma'am.
not clear? Yeah. So that means this is GH is equal to H, but GH is equal to H implies that G belongs to H. That means if I start with any element in the kernel, then it says that that element belongs to H. That means K is a subset of H. So that means this index cannot be equal to 1, because if this index is 1, that means G has to be equal to K. But K is already sitting inside H, and H is a proper subgroup we already know. So that means this has to be strictly greater than 1. Is it clear now? Yes or no?
Yes, ma'am.
Okay. So now what we have already seen, that there are two choices for the index. Either it has to be equal to 1 or it has to be equal to P. And we have seen that this is strictly greater than 1. That means it has to be equal to P, right? Thus, G colon K is equal to P. But what does that mean, that G colon A is equal to P? Now you have K sitting inside H, sitting inside G.
H equals to K.
Yes. And you know that G colon K is nothing but G colon H into H colon K. This is equal to P. This is equal to P. Therefore, H colon K is equal to 1, which implies that H has to be equal to K. Therefore, K is a, or H is a normal subgroup. Is this proof clear? Is this proof clear to everybody? If not, then you can tell me which steps are not clear. I will try to explain once again. You don't have to hesitate if some steps are not clear, because these are non-trivial things. Any doubt?
Hello, ma'am.
Yes.
Ma'am, in that step, index of G colon H equal to 1 or power of P, from which we apply it.
This statement, how we are getting this?
Yes,
Is
ma'am.
this why G colon K is equal to 1 or a power of P? That is your question?
Yes, ma'am.
Okay. What is G colon K? That is order of G divided by order of K, right? Isn't it?
Yes, ma'am.
What is the order of G? G is a P group.
Yes, ma'am.
So now what it will be, order of G divided by order of K. So order of K has to be again some multiple of P. So if after dividing also I should get some power of P only, na?
Oh, okay, ma'am. Okay.
Okay. Yeah. Any other doubts?
No, ma'am.
Okay, fine. My time is almost up, so I will just finish with one more theorem that I will state. You please try to do it by yourself, and if you are not getting, then in tomorrow's class you let me know. I will first discuss this and then go to Sylow's theorem. This is very important, and somebody I think already asked me this question. So let G be a finite group with order of G is strictly greater than 1, and P be the smallest prime factor of order of G. Then it says that any subgroup of G with index P is normal. So if you compare this result with the previous one, now here we don't have the restriction that G is a P group. I have just started with a finite group, okay? But now here this P I have a restriction. I am calling this P to be the smallest prime factor of order of G. If this is the case, then I am saying that the index P subgroup will be a normal subgroup. So in some sense, it is the generalization of the previous theorem from P groups to any other groups with a restriction on the prime, okay? And you can also see it is a generalization of the fact we have proved that any subgroup of index 2 was in fact a normal subgroup. It is a generalization in that sense, but here P is the smallest prime divisor of the order of G. Okay. Is Harshvardhan present today?
Yes, ma'am.
Yeah. So I think you asked me this question.
Yes, ma'am. Yes, ma'am. I had asked this.
Okay. So the hint for this one is the same group action. Okay. So I will just, you try, tomorrow we will see. So I will consider H be a subgroup of index P. Okay. Now I will consider this group action on the set of all left cosets. You already know the left cosets. This will give you, so this is the group action that I have already discussed. Now the permutation representation of this group action, it's almost similar. Okay. And then what you want to show, again the same thing, that kernel of phi is equal to H. Try to show this in this case. Okay. If you are not getting, tomorrow I will discuss. Think about it. This is the hint. I have almost done. Only in the last couple of steps, you have to use the fact that P is the smallest prime divisor. That's all. Okay.
Yes, ma'am.
Okay, so I should stop here today. So I have not yet uploaded the next tutorial. I will upload it. So maybe we will discuss the tutorial sheet in next week, Wednesday. And if you have solved some problems by this time, then we can discuss on this Friday 1 hour lecture also. The syllabus will be till the Silos theorem that I will be covering this week. Okay, and next week, Friday, we will have the class test. Okay. Any questions or any doubt?
That would be the same pattern like earlier.
Yeah, it will be of the same pattern. Okay.